I'm Robert Bergeneau, the Chancellor of UC Berkeley, and also, although I hate to say it in such august company, a professor of physics, but just an ordinary professor of physics. Today we have a very special event to bring you the absolute best that only a preeminent university like Berkeley can offer. A discussion by 6 Nobel Laureates on one of the greatest challenges facing America and the world today, energy self-sufficiency in the 21st century. Before I introduce our Nobelists, let me tell you a little bit about Discover Cal. The Discover Cal lecture series began in 2003 as an opportunity to bring together our alumni, Cal parents, and friends in Southern California to hear from Berkeley's renowned faculty and campus leaders about the important and exciting leading edge research happening at Cal. And indeed, Mary Catherine and I have had the pleasure of participating in a number of Discover Cal events in Southern California, and we've even taken them to New York and other places. But it seemed only appropriate to make these exciting events also available to the community in Northern California, where Berkeley is, after all. And so today is actually the first in our program in this newly expanded series of Discover Cal, the first in Northern California. As a great teaching and research university with a public mission, and I emphasize public mission, we have an obligation to bring our immense intellectual resources to bear on some of the most difficult challenges facing society today. Whether it be the eradication of neurodegenerative diseases like Parkinson's or ALS, the elimination of global poverty, or the suppression of global warming, Berkeley researchers are playing a leading role. In the complex world in which we live, there are no simple solutions to these great challenges. To meet these requires attention from many different disciplines. Berkeley is especially well situated to address such multidisciplinary challenges because of the unusual, phenomenal breadth and depth of expertise on our campus. Among our country's most serious concerns today are national security, long-term economic competitiveness, and the dangers of global warming. Energy is at the center of all of these concerns. With our close partnership with Lawrence Berkeley National Laboratory, we are uniquely positioned to become leaders in energy research and to make real advances in tackling our energy problems. Together, we can offer unparalleled expertise and resources in the areas of alternative energy research and policy. As many of you may have noted, in its recent proposed budget, Governor Schwarzenegger has included a $95 million research and innovation initiative to help keep California on the leading edge of global competitiveness. A good portion of that funding will go to support research aimed at solving our energy problems. Specifically, Berkeley and Lawrence Berkeley National Laboratory are part of a consortium partnering with the University of Illinois at Urbana-Champaign in a $500 million proposal for the British Petroleum Energy Biosciences Institute, which will focus on the development of biofuels and carbon-neutral sources of energy. At Berkeley, we currently have 7 Nobel Laureates on our faculty. They are part of our proud Nobel tradition of 20 Nobel Prize winners on our faculty and 24 of our graduates who have also won Nobel Prizes, and there's no double counting, YT. This tradition began in 1939 with a Nobel Prize to Ernest O. Lawrence for the invention of the cyclotron, and has continued right up until today with the 2006 Nobel Prize in Physics to Professor George Smoot. Today, we will hear the different perspectives of 6 Nobelists on energy self-sufficiency, 4 from physics, 1 from chemistry, and 1 from economics. The discussion you will hear will be representative of the caliber of teaching and intellectual rigor to which Cal students are exposed. As all of you know, Cal students are among the most talented in the state of California. 99% of our freshmen graduated in the top 10% of their high school class. About half of our students are from Northern California. Notably, and reflecting our public mission, about 1/3 of our undergraduate students come from families whose family income is under $35,000. Indeed, we have more undergraduate students on the Berkeley campus from impoverished backgrounds than all of the Ivy League schools put together in total. As a public university, Berkeley makes an academically elite education available for all of California's top students, regardless of their backgrounds. And these outstanding students deserve no less than the very best education. At Berkeley, we place our finest teachers in the classroom. And I'll tell very briefly an anecdote which poor George has been subjected to several times. 2 nights after he won the Nobel Prize, we quickly organized a celebratory dinner at the Chancellor's house, and we had all of the rich and famous there to help celebrate George's prize. George was sitting beside me, and we were about 2/3 of the way through the dinner, and I noticed he was getting nervous, and then more nervous, and then more nervous. And I thought, well, he was thinking about, meeting the princess or the queen in Sweden or such like, or the king. And it turned out he was getting nervous because he was lecturing freshman physics in the morning and he hadn't yet prepared his class. And finally, he just turned to me and said, I just can't stay anymore. And he got up and left to work on his freshman class. I mean, where at Berkeley, where else except at Berkeley could that happen? Tell me. Just as important as the Nobel Prize winners you see before you, here at Berkeley, overwhelmingly, our approach to faculty is to hire extraordinarily talented junior faculty members who we hope someday will play the same leadership roles in their field and win honors like the Nobel Prize or Pulitzer Prizes, etc. Indeed, today, right now, we have 28 MacArthur Genius Award winners on our faculty, and 92 Sloan Fellows who represent the very best young physical, life, and social scientists, researchers in North America. So we have not just this incredible battery of outstanding senior, look down in the end, I think you all won't be insulted by being called senior scientists, but we have also an extraordinary coterie of very, very talented young people, all of whom who are doing wonderful research and scholarship and who are also in the classroom. Of course, we're able to sustain the excellent research and teaching that we do here at Cal because we know we can count on the generous financial support of our alumni, parents, and friends. In the last fiscal year, the campus raised a record $347 million of private funding from more than 61,000 individuals, and this is an all-time record for Berkeley. So that was 61,000 of you participated, Now, we have an actual alumni population of 415,000, so you can do the arithmetic and imagine what would have happened if everyone had participated. Your help, your support helps Berkeley's students and faculty pursue their work across the campus and around the world. It also helps Cal to reach out to future generations of students. Through your support, UC Berkeley can continue to generate the kind of talent and ideas that set it apart as the most distinguished public teaching and research university in the world. So now, without further ado, let me proceed to introduce our Nobel laureates. I'll introduce them all first, so they can then come up and speak. And I'll do so in the order in which they're going to speak in our program, which is also the order on the table. That's because otherwise I'll get confused. Each Nobel laureate will speak for 10 minutes, after which I will invite them to comment on their colleagues' perspectives. And we will then take questions from the audience, and I want to say now, no questions about the oak trees. Our first speaker will be Stephen Chu. Steve is the director of Lawrence Berkeley National Laboratory. He received his Nobel Prize in 1997 for developing methods using laser light to supercool gases and create atomic traps, atom traps, pardon me. His work has allowed for individual atoms to be studied with great accuracy. As you will discover if you don't know already, Steve is absolutely passionate about bioenergy and trying to replicate through synthetic biology nature's process of energy production through photosynthesis. He has dubbed the project Helios, which is the Greek word for sun. As you already heard, George Smoot is our newest Nobel laureate, who received the physics prize just this last month in Sweden. An astrophysicist, George headed a team that was able to image the infant universe, revealing its newborn form and the patterns that have helped shape the universe ever since. He was one of the first pioneering astrophysicists who devised ways to conduct experiments that produced data and information about the early universe. Charles Townes received his Nobel Prize in Physics in 1964. Charlie's research into the properties of light led ultimately to the development of the laser, a tool that has revolutionized industry, medicine, communications, and really all of science. Just over a year ago, the university celebrated Charlie's 90th birthday with an overwhelming audience of scientists from around the world who have been influenced by Charlie's work. I remember walking into the reception, and there were two people who I think the day before had won Nobel Prizes themselves, one from the East Coast and one from Germany. And their respect for Charlie was so high that they basically skipped all of their local celebrations and came to Berkeley to honor Charlie, which I think was an extraordinary tribute. Dan McFadden won the Nobel Prize for Economics in the year 2000. Daniel studies econometrics, that is analysis of data at the micro level, and developed a method for examining behavioral patterns in individual decision-making. A deep interest in social welfare drives his research. One of the applications of his statistical tools included measuring the economic damage to individuals from an oil spill, and specifically the infamous Exxon Valdez spill in Alaska. Dan actually started out his career as a physicist, but decided economics would be more relevant to human society. We can debate whether or not that's true later. Let's see. Next is Yuan T, who was the 1986 Nobel laureate in chemistry, and he took the work that Charles Townes had done steps further. His designs and experiments with molecular beam devices sent streams of intensely packed molecules into each other at supersonic speeds. Scientists were then able to view chemical reactions and discover, sort of a very fast timescale, molecule by molecule, and discover how and why they take place. This knowledge has contributed to today's powerful lasers, as well as contributing immensely to our understanding of the fundamentals of chemical reactions. I actually probably every time YT wouldn't know this, but every single time I speak to graduate students or new graduate students, I actually quote YT, and he once said, and I hope this is true and not just apocryphal, you can confirm it afterwards, since I've been quoting you since I came to Berkeley. He said, "I came to Berkeley as a graduate student because of the faculty. I returned as a faculty member because of the graduate students." Graduate students like to hear that. Did you really say that, YT? Yes, good. Our final speaker will be Don Glaser, who received the Nobel Prize in Physics in 1960, when I just learned he was in his early 30s. Now that's a pretty fast start. He invented the bubble chamber, which is based on a simple observation, I'm told, and you can also tell me if this is apocryphal or not. The idea is purported to have come from observing track left by a stream of bubbles in a bottle of beer. It's apocryphal, but it's a great story. No matter how the idea came to him, I also learned that as a graduate student. Graduate students love stories like that. It justifies spending your whole evening in the bar. His invention allowed scientists to track the movement of atomic particles and marked an important step in the exploration of the fundamental structure of matter. Unfortunately, our 7th Nobel laureate, George Akerlof, who won the Economics Prize in 2001, was not able to join us today because of a family obligation on the East Coast, and so which was a long-standing obligation, so he just couldn't be here, and he apologizes. So enough of me. Let me now turn over the floor to our very distinguished speakers, beginning with Steve Chu.
Okay, thank you. It's a pleasure to be here, and so I just want to push on. I wanted to add one word to the title of this symposium, and it's clean energy self-sufficiency. We can become self-sufficient in energy in terms of substitutes for oil by taking coal and liquefying it, but that would be an unmitigated environmental disaster if we did that. U.S. oil production has been increasing, but the imports of oil have been increasing to the point where it's now 60% of our total oil. But perhaps many of you in the audience don't know that the United States was an oil exporter until 1970. It was the primary producer of oil in the first half of the 20th century. A similar history, only even more so, is being followed by China. China used to export oil, but in the early mid-90s, it began to import oil, and now imports roughly half of its oil. As we go forward, there's a lot of jockeying for position among countries with rising economies to gain access to this very precious fuel. And it is becoming a defining part of the geopolitical strategy of all countries. In terms of cost, in 2005, we spent $250 billion importing fossil fuel. That, if you compare it to, for example, the total U.S. balance of trade, it's 1/3 of the entire deficit in balance of trade. And as years go further on, this is going to increase. And so economically, we have to take note of this. But the thing that's most compelling to me, and the reason I have become so passionate about the energy problem, is that the Earth is warming up. That's not a matter of debate, that's a matter of measurement. The red curve is the temperature of the Earth since 1860 till now, and the gray is a model of how this could have occurred if it was due to variations like changes in solar intensity, volcanoes, other things, natural variations. And you see we can't explain it. But if we include the greenhouse gases that humans have put up since the beginning of the Industrial Revolution, we have a good plausibility argument that indeed this warming has been caused by humans. And in the last 5 to 10 years, models have gotten better and better, and this is becoming more and more compelling that, yes, indeed, the increase we see is due to humans. So what are the predictions of what this might be? You've heard of many of them, but I want to stress two that perhaps one is not as sensitive to. And that is, what's going to happen to the water supplies of the world? This is a paper published in 2004, where on one column you see aggressive control of greenhouse gases. That is to say, one really takes hold of it, does things even more aggressively than what was proposed in Kyoto. And under this scenario, in this century, the snowpack, actually this is, I forgot, there's, let me see if I can do this. Aha! Sierra snowpack will decrease by 30 to 70% in the least alarmist scenario, and by 73 to 90% in the most alarmist scenario. And the alpine forest will also decline. What does this really mean? This really means that the water storage in California is at risk in the least alarmist model, and one that I personally think is way over optimistic. Okay? And this is going to happen all over the world. And in the most alarmist model, we're going to have a serious drinking water problem. Forget about agriculture. Forget about the ski industry. And so this is some of the things that are being predicted now, and this spans the gamut of predictions. So science has not actually decided what is really going to correct, and it's true, and you may hear that science hasn't really landed on a firm prediction, but the predictions vary from bad to really bad. And that's where the uncertainty is. Here's another prediction, and it has an uncertainty. Suppose we actually take the CO2 and we actually get control of it and decrease the amount of CO2 humans emit and greenhouse gases by a factor of 20. Will that solve the problem? Well, it depends on when we do it. Because the prediction is the amount of carbon dioxide and other greenhouse gases we put in the atmosphere, that will linger for between 100, 150, and 1,000 years before the natural processes of the Earth actually reclaim that additional carbon dioxide. So what we do today, and for the next 20, 30, 50 years, will have a history of somewhere between 150 and 1,000 years from now. That's where the uncertainty is. Is it 150 years, or is it 1,000 years? So let's take an average, 500 years. We haven't done anything in terms of pollution that has a 500-year time scale. We've polluted streams, we've polluted air, but after 10 years, it can be cleaned up if we stop polluting. This is something that will be a century to a millennium. So if you say wait until you're really sure, then it will be too late. So now, I hope I've raised some concern. The good news is we can do something about it. We can actually do much to maximize energy efficiency and minimize energy use. And Lawrence Berkeley Lab has been a pioneer in this for the last 35 years. But what has captured the excitement of both the Lawrence Berkeley Lab and UC Berkeley is that we can also develop new sources of clean energy. And just to remind you who are not familiar with the lab, it's in a hilltop overlooking the Berkeley campus. It's a very distinguished lab. 11 of its employees were awarded the Nobel Prize, and even more important, 9 of them did their Nobel Prize work at the laboratory. Berkeley has 20 Nobel Laureates, 15 are in science, and so 11 of those 15 did their work, were associated with the laboratory, and 9 did their work there. Right now, 3% of the membership of the National Academy of Sciences are employees of the laboratory. And so it's safe to say that part of Berkeley's great distinction is having Lawrence Berkeley Lab next to it, and it's also safe to say that part of Lawrence Berkeley Lab's great distinction is having Berkeley next to it. We have, over the last 2.5 years, begun to discuss a big program to harness the energy of the sun in various forms to create transportation fuel for energy independence. And it can come in various forms. It can be the sun growing plants raised for energy, not for food, and then converting the plant material into a liquid fuel. It could be a new generation of solar photovoltaic cells to generate electricity, and that can be used as electricity. But even more importantly, you can want to also convert electricity, whether it be from photovoltaic cells or wind or any other form, into a transportation fuel. And if, for example, we had inexpensive, efficient solar cells at a very modest efficiency, something on the order of 15% efficiency, but cost-effective, this is how much land you would need, and we can plop it anywhere in the desert areas, that could satisfy all of the United States' electricity needs. It's not very much land, and there's lots of uninhabitable desert areas in the United States. One of the things is that we have a nanotechnology center run by the government, has a yearly budget of $20 million, and one of the things is we would like to harness the scientists and science that can come out of this nanotechnology center to develop a whole new generation of photovoltaic cells that could lead to very inexpensive and efficient photocells. The other thing is that we think that there are great opportunities in biofuels. First, there was a huge improvement in agricultural efficiencies over the last decades. Between 1930 and this year, the average production of corn in the United States has increased 8-fold per acre, not per farmer, per acre. And similarly for other crops. And in fact, worldwide, the average productivity of agriculture has increased 3-fold per acre. And so we can feed the world's population today, and in the peak of the population of scale 9.5 billion people in the middle of this century, and then it's projected to decline, we can feed the world's population. And in fact, not only that, we will have excess capacity. The United States currently has, of scale, 60 million acres taken out of production because of excess capacity, and that will increase. So what can we do? We can develop a new set of plants and get the same improvements that we've gotten in corn and soybeans and other plants. These plants would harness sunlight, carbon dioxide, and water to make biomass. They can be self-fertilizing in many cases if we do it right, and drought and pest resistant. They will be much more economically friendly than our current agricultural processes. We get the biomass, and we'd like to convert this biomass much more efficiently with less energy investments into chemical energy. There are many ways of doing this, and the most exciting thing about this is that many of the frontiers of science will enable us to do this in a much accelerated way, so we don't have to wait 70 years to get these improvements. Perhaps 5 to 10 years is more the time scale that we expect today. This is an example of what we can do. This is a cartoon of a termite and eyeing very greedily a house. Termites eat wood, and yet if a termite eats wood, it can't convert the wood into the energy it needs. So it struck a deal with communities of bacteria within the guts of a termite. This is the gut of a termite. And these microbes will actually digest the wood, turn it into an energy source that the termite could use. There's a little carrying charge. They use some of that energy for their own survival. And the deal they struck with the termite, we'll give you the rest of the energy. You go find us more wood. And so there you have it, a very nice thing, and they find your house. We are sequencing these bugs, these microorganisms, to figure out what they're doing so efficiently, and with that knowledge we hope to make a new generation of microbes that can not eat your house, but to convert biomass much more efficiently into energy. Why do we think we can do this? Well, there's an existence proof. Malaria is a great killer, kills between 1.5 and 2 million people a year. It was anticipated it would kill far more people because the protozoa that causes malaria has become resistant to the quinine-based drugs. Luckily, there was a cure discovered, and it's an extract from a plant that grows in Southeast Asia. And a scientist at the Lawrence Berkeley Lab and also a professor of chemical engineering and chemistry here at Berkeley, Jay Keasling, has taught bacteria to actually produce this chemical that can be turned into the drug. It's not a single gene, but it's a whole set of genes. So it's what you call synthetic biology or systems biology. For those of you, that's Jay Keasling. He's now director of the Physical Biosciences Division of the Hill. Is this practical? Well, it's got the eye of the Gates Foundation. And in the last 2 years, the Gates Foundation has given Jay and a startup company, Amyris, $42 million to make it into production, from the laboratory into wide-scale production. They had a business plan. They have exceeded all the goals of the business plan. They're ahead of schedule. And they believe that in 1 or 2 years, they can deliver to the patient at 20 cents a cure this drug. The same technology that produces this drug can produce biofuels. And because of that, Amyris, this company, has now begun to get venture capital money to do the same for biofuels. These microorganisms can digest the cellulose in principle and make a new set of fuels. I'm going to skip the fact that we're raising money for a $30 million building from various sources. State of California, as Chancellor Bergenow mentioned, is investing $40 million if we get the BP proposal, and an additional $30 million whether we get it or not. The University of California is willing to use its borrowing capacity to allow us to borrow another $30 million. We've raised already $15 million and are hopeful to raise another additional $15 million. So if any of you want to chat with me afterwards, I'll be happy to talk. This year, 2007, we've raised $4 million to actually start the research. As we convinced the government to turn up the government funding sources, and they are doing this in a very serious way, we want to get started today. There is no time. And so already individuals have given $4 million in research money, so we don't wait for the building. We start today, and so on and so forth. And some foundations are extremely interested in what we're planning. In the end, though, it's not about buildings. What we want to do is about people. And if you look at the great interdisciplinary efforts that have achieved success, things like the Manhattan Project, like Bell Laboratories and its invention of the transistor, the invention of radar. In these situations where you need to bring scientists from variety of disciplines, including the engineering sciences, what was their success? How were they able to do this? And what we're trying to do now in the so-called Helios project is to mimic that success, that individual genius is nurtured, but once there's a person who has a great idea, that they are encouraged to form quickly, self-assemble into teams. If a person has a great idea in their 20s or 30s, let that person be the leader of the team. Don't give it to a senior professor who's in their 50s or 60s. In fact, George Smoot, when he started his Nobel Prize-winning project, he was in his late 20s at the laboratory, and he became the group leader in his early 30s. Another great discovery that's garnering equal amounts of attention, that person started in their early 30s. Feynman at the Los Alamos laboratory became a group leader of a theory section when he was in his middle 20s. So this is something we really want to do, that we want to get the best people be in charge of these ideas, but still managed by top scientists, but top scientists who have intimate expert knowledge. And you want people to be bold, take some radical approach. That means you're going to fail. But we want to invest in people, not an idea, because the really bright people, if you have the tools to get a really good idea, okay, that didn't work, move on to the next idea. And eventually it works. And this is, again, a different model. That's how it was done at Bell Labs. That's how it was done in the Manhattan Project. And this is how we have to do it in order to solve the energy problem. And so it's ideas like that that have really excited the Berkeley campus and Lawrence Berkeley Lab. And I hope it'll work. Thank you.
get a little help here. I want to thank you guys for all showing up. It's a pleasure to be here. And I have a different approach. I learned when I got back from a trip at the beginning of this week that I was going to be an expert in energy self-sufficiency. So I thought I would do it a different kind of talk. And you can see why I needed my preparation for for my student class the next morning. So I put on my first slide the cover of Energy Self-Sufficiency newsletter. These kind of things exist all over, even when I was a kid. So I'm going to say something at the beginning of my talk. I'm going to give what I call walk to walk, that is establishing my bona fides, and also making you realize this is actually a human endeavor, individual human endeavor. So there's a phrase from the old days that you'll remember, which is think globally and act locally. And in the end, we'll see economics is the only way that we actually do that really efficiently. So that's for Daniel. And then I'm going to go and talk about something that you guys will think is controversial, which is nuclear power. And so I have to establish my bona fides first. And so when you're young and idealistic, you think, wouldn't it be great if I lived off the grid, you know, and I did everything myself? That is, I don't have to go to the Arabs and ask for oil or something. And it's a different level of off the grid. And, it's going to be a while before we have devices you can buy and put on your roof and plug them into your wall socket and give the extra power back to the grid and supply whatever you want. So what are we going to do between now and then? So you want to learn the difference between what is it you desire or think you wish you had and what you need and so forth. And so I hark back to my own experience. My parents' farm had a windmill, right? And it had to, because sometimes you're really off the grid. We lived in Alaska and so forth, and different other places. And there were times when you didn't have power and you needed other alternate sources. But if you live in an urban area, you're almost never better off being off the grid. My mother, everybody has the same thing. My mother had an oil well pump on her land. She didn't own an oil well. She just had the pump, right? And she got $500 a year for that, but that's it. My parents also had a motor generator set because if you don't have power, sometimes you need it, right? So when you have to run that, you start realizing the power company is much better, right? So my experience is, you know, not have to get up in the morning and go out and break the ice and bring the water from the well and, you know, and turn the motor generator set on and so forth is a better way to live than doing that, you know, using the power company is a better way. And so I found the power company is the best, and I really care about having my refrigerator, my microwave, my stove, because I'm not personally energy self-sufficient. I like to have food, although I'm hoping Jay Keasling can learn to give me chlorophyll so that I can I can just feed directly, and then I'd feel better. And lately, I like to have lights in the computer and the internet. So, and not only that, I have broadband internet, and I have my computers on more of the time. And when I get to have my own avatar, what I realized by reading about it is that currently, unless we improve energy efficiency, my avatar will use about as much energy as the average person in Brazil. So, you know, if you're thinking about extending your life by going into a computer, it's still not zero impact on it. And so the other thing that happens, I've actually been serious about energy conservation and paying attention. I have energy use records for almost 40 years. And what I have found is my energy use is generally kept at a low level, much lower than the average for an industrial, you know, for the US and so forth. But it has increased with my GDP and my age, right? And it's because you got more money, you buy more stuff to try it out and so forth. But also as you get older, you like more comforts and so forth. And so the trends for me personally and the trends for the country as a whole are pretty much the same. As the GDP has gone up, the use of electricity has gone up, and it's gone up faster than the use of energy. That's we're conserving energy more, but we're moving into using more electricity for some of these forms, right? It's one of the things that happens. And this will become relevant when we get to the second half of my talk. Okay, so here's some of the data. I was going to put my last 10 years, but it gets pretty complicated because every time I moved into a place, I started making it more energy efficient, and it got to be okay. So if we were really being serious to tell you how it was, when I first came as a postdoc and I had a nice apartment and I did the weather stripping and all that kind of stuff, my PG&E bills went down to $2 to $4 a month in the summer and up to as $10 to $15 a month in the winter, right? So you have some idea what that's like. But you can see on here a plot, the red one is the electrical usage in kilowatt hours. And you can see when PG&E and Costco made, you know, these compact fluorescent energy saver bulbs, and I went and replaced all the bulbs in my house on that thing, my energy usage dropped by a third. Right? It was quite impressive and so forth. And when I took on a housemate, my energy usage went way up. And you can see the seasonal I had a friend who was in a house that got sold, and he was desperate, and I have a downstairs that was unused, so it worked out. But we have completely separate households, but the utility bills come in the same place. And it's interesting to see how that developed. But you can also see below that, although scaled down by a fairly big factor, the gas usage, and you can see how seasonal that is. And then you have to realize the weather. To really analyze this, you have to see the degree days. You know, some years are colder than others, and so forth. And the reason I cut off the end instead of showing everything up to date is that there was floods and a bunch of other stuff, and I had a dehumidifier running for a while, and so it skews the distribution. And so what happens is, in my own personal thing, you run into the same thing you do when you're doing the national thing, which is you make improvements and things get better, but then there's a lot of the factors that go on. But this is a thing that you guys all have to do. I also drew 2 lines on there: the mean power used per capita per month for the world and for the developed countries, and you'll see in some of these charts that people will show you the U.S. is worse than that. California is closer to the developed countries average than the rest of the United States. We're particularly bad. But you can see I've made an effort to keep my total energy usage per year at a fairly low level, just because I've been concerned about energy since I realized we had a crisis, and that was back in the 70s, right? And so we can see. So I've been using the high efficiency lights, and I've been managing the lights. It matters whether you turn the lights on or off, surprisingly, right? Just like, Jimmy Carter told us to wear sweaters. And putting in an efficient refrigerator works a lot. In my house, they were putting in the downstairs where my housemate lives, the people who had the house before, a solar-powered refrigerator. And I sold it to them when I bought the house because it's too big and clunky. You still, you got to live too, right? And so it has great huge thick walls and in very little useful space. The technology isn't ready yet, but it has to get to be evaluated. The other thing that I use a lot of energy for is the heating and weather stripping, insulation, honeycomb shades, which some of you may not know, would turn out to be cheaper than putting in them. And I've also gone to passive solar heating. So one of the first things I did this morning when the sun comes up, because the hill behind me comes up a little later, I open the shades on the south side of my light, and 1,000 watts comes streaming in, and my house gets much warmer and so forth. So I hate it when I have an 8 a.m. class in the spring, like I did last year, because the house is cold when I get up in the morning, right? Because I only heat the bedroom at night. So the other thing I did is I have added a solarium, and that's another thing, and I've improved the furnace and done the insulating out here. So I show you a picture of the solarium as it's being constructed, and you can see the problem is the money, the problem is the city of Berkeley and getting the permits and so forth. So you'll notice there's no wood in here. It's it's all metal and glass to the floor to ceiling and so forth. So there it is on the back of my house, so you can see how it looks. So, and that works. That made a big difference in my life. And so the other thing I do is I walk the walk of walk the walk, which is I have a 1986 Toyota Camry with about 100,000 miles on it. And that's about 5,000 miles a year, but I actually only put half of them on. I had a girlfriend that commuted in it for a while because she had a job in Silicon Valley, and she put about half the miles on. And so I typically go to the gas station about once per month. I believe the last time I went to the gas station was either late November or early December, but I had been out of town. I was in Sweden part of the time, so it's But most people can't be as extreme as I can in this situation, because I still believe you have to live a reasonable life, and that's part of what I'm saying. So Nobel parking, a big deal was made about Nobel parking. That was the first thing the chancellor mentioned when he saw me, right? After he said, congratulations, it was, all right, you get your parking space. Okay, I didn't choose the place that was most convenient. I persuaded the dean to move his parking place over so that we had a place where there are 5 Nobel Laureates in the world, because I figured that would be really impressive to visitors. What I really found out is this made all the other people on campus mad, because they see these empty parking spaces, because there's almost never any cars parked there. And occasionally, because Nobel Laureates or Fields Medal Prize winners apparently don't pay that much attention, I find a Prius parked in my space because he just moves up to the #1 NL spot, And so here's a picture I took yesterday morning just before 9. You see the NL spots, right? So NL laureates don't use that much energy, They're busy thinking, right? No, but, so I was here, I just didn't have my car here, you know. So, okay, so now I want to go to nuclear power. And so what are my credentials? I don't have many credentials, except I was on American Physical Society Nuclear Reactor Safety Committee, and we were reviewing whether nuclear reactors were a reasonable approach for what the country should be doing. And we did studies in the early 70s, and we reported in 76. And some of you may remember why this happened. There was an oil crisis in 1973, and it was the declared national policy that we would become energy independent, that is, energy self-sufficient in a clean way. And one of the things that people thought was okay would be nuclear power, but people were concerned about the safety of it, and so they wanted independent people to do that. And so I was on a committee headed by Hal Lewis from Santa Barbara to review this and give independent stuff. And so we studied it, and we said it was safe. Of course, you'll realize 2 years later, something interesting happened. But we were still right, but now I have to explain. And when you get into explaining, you're already in trouble. Okay, so why nuclear power? Well, let me say this to start with, to give you some stuff for it. The issue is that 99 and 100% of the energy that humans use ultimately came from nuclear power in a very direct way. Okay, so now we're only arguing about the source, whether it's the sun, right, you know, through fossil fuels or something, or whether it's man-made, you know, nuclear sources, right? Okay, in this case, it's going to be a significant source for national needs. It's a relatively long-term source, even more so than coal, although economically coal and nuclear power are the two serious competitors in terms of what's going on these days. It really helps significantly with the greenhouse gas issue, and I want to have air conditioning because I believe it's going to get warmer. Right? And I'd like to have some electricity, you know, even though I've tried to keep my own use down and so forth. The good thing about nuclear power is it can handle a very significant proportion of the baseline. It can't handle it's not good to ramp them up and down, so you need to hold a baseline and then have something to hold the excess and so forth. And the real issue is the issue of public acceptance. So the public response has been really a serious situation. So I give a quote that's out of an article from last year from the City Journal, which is a New York City newspaper. It's talking about, you know, how people promised back in the 70s how nuclear power was going to solve all our problems and make energy cheap and so forth. And it says, in this now standard histories, the beginning of the end of the nuclear power arrived on March 28, 1979, with the meltdown of the uranium core at the 3 Mile Island, Pennsylvania. The Chernobyl disaster 7 years later drove the final nail in the nuclear coffin. Okay, so the thing that you have to do is, that is in some sense true, but it's also in some sense not true. Nuclear power plants account for 80% of the electrical production in France. In 2005, there are 104 U.S. commercial generating units that are fully licensed to operate, and together, actually 103 of them do about 20% of the nation's electricity. There's one of them that's not really turned on these days. Okay, so how do we reconcile the fact that this is going on, right? That it's the end of nuclear power, and yet we get 20% of our electricity from nuclear power. How do you reconcile that? Well, let me show you one picture. This is one of the nuclear reactors in California that I actually personally visited in the 70s, and it's still there, and it's still the same technology, right? It's still, so one of the issues is when the public response and 3 Mile Island together essentially stopped nuclear reactors from being built after that. So all the nuclear reactors we have and all the staff that we have for them, they're all the same. They all got hired in the 70s and trained in the 70s for the most part, and we've been living off of that since then. Okay, so here's a plot of what's happened about the generation, comparing oil to nuclear, right? Because you remember in the 70s we had the energy crisis, and people tried to switch away from generating from oil and put more nuclear stuff online, but you'll see there was a rise, which in normal sense should come up exponentially and then flatten off as you get to 80 or 85% of the load capacity, like in France. But in fact, it rolled over at 20%, and that's because no new licenses, you know, no nukes in my neighborhood, and like, of course, we're in Berkeley, no nuclei are allowed in Berkeley, and so just don't tell anybody. Yeah. And so what you see is the beginning of what I would say is a disaster, but I didn't want to write the word disaster in there, so I wrote crisis. On a scale that's comparable to that of the Vietnam War or Iraq II, That is, if you look at how much money was spent on the Vietnam War, it's on the order of $100 billion in 1970 dollars, and in Iraq too, which is about $400 billion in current dollars, the investment and the loss of investment money in nuclear energy is on that sort of same scale. And because of the public reaction, we have really impacted our capability for the future. We may have to actually purchase stuff from the French, God forbid, right? We have an issue about engineering expertise. We don't really have that many new or modern designs and upgrades for our reactors. And we're in a situation where our manufacturing and operations capability is compromised, and likewise our oversight and regulation is compromised. And yet the nuclear energy is one of the ways, and we're going to maintain a high standard of living in the future. So, how are we going to fix this, right? Well, I got some recommendations. This is what being a Nobel laureate is an expert, but I haven't thought these out that carefully. We have to actually address the public's acceptance concerns, and one of which is explaining why, the number of people who died from 3 Mile Island was actually quite small, namely 0, right? And which is, not that high a number. And in fact, the safety stuff did work the way it should have. It's just, it was a public relations disaster, and it led to disaster. Now, Chernobyl made things a lot worse, right? Because there, people deliberately went in and tied off all the safety things and made bad decisions, and then continued to make a lot of bad decisions and did kill people and sent people in to clean up the mess and killed them too, right? And so it was not a very good thing. So we have to choose to make this a national energy priority. We have to develop the new nuclear engineers programs and the technicians and the operators and so forth. One of the things that's happening is in the next 6 years, roughly 50% of the people in the nuclear industry are set for retirement, right? If they got hired in the 70s, they're going to retire, right? So they have to be replaced in some way, and they got to know there's a few people who are going to come in and got to know there's a future. Or otherwise, we're going to be shutting off old reactors and we won't have anything to replace them and so forth. And one of the suggestions I have that's probably more controversial is that I think that we should license only 4 or 5 companies to build and operate nuclear power plants, not the 70 independent utilities. We should have those 4 or 5 companies build and operate nuclear, build them in parks and operate them and sell the power to the utilities. Right now we have 24 utilities that are generating nuclear, electrical power, and I think regulating those and supervising oversight for that is just much more difficult than it needs to be. And there's no reason that 70 utilities should have to have nuclear expertise. They should have electrical utility expertise and so forth. So if you do that, have 4 or 5 companies and have nuclear power parks, you can have a lot of things that help you with the operations, the safety, the security, the regulation, a lot of other stuff. And we also need to have a program of research into advanced and more modern reactors. We might as well be more efficient. When I went to Diablo Canyon, I was very impressed that the display panel was human engineered for 1970. Right? So you can sort of imagine. There was a meter that went 0 to 1 gigawatt, right, for one of the things, and another one like that. I mean, that's not the kind of heads-up display we'd have today. Okay, so here is a chart from the National Energy Institute saying what their vision is to have emission-free electricity, which is now 30% carbon emitting, to get to 31% by 2020. You'll notice that coal still went up a lot, right? The total power that they assume we're going to need, which I think is probably true, is gone up. The fossil fuels going to go up. That's a big issue there. But just to keep it 31% is going to require the program that I'm already outlining. Never mind to get to 80% or something in the future. And I've shown one other chart before I finish up, which is what are the sources of emission-free generation? Well, you talk about wind, you talk about hydro and solar and geothermal and so forth. Nuclear is already 3/4 of it. And if you think about what's going to happen in the future, the only thing that can produce anything on the scale that we're talking about, until we actually have the only technology we have in hand is nuclear technology that can do it. Until we get the solar cells or the other things, we're just not in the position to do it yet. And so the question is, if you got to have the stuff working by 2020, what are you going to be building in 2010? Stuff that you know how to build or new stuff, right? So, okay.
Well, I'm not a specialist in this field, but I do have some views, and I'm going to share with you. Can you hear me in the back all right? Hear me? Good, thank you. This is an important area we're discussing, certainly. A very important area. It's also an important part of our economy. Energy costs is about something over $1 trillion a year, 8% or more of our total GNP. And then in addition, there's pollution, which in the long run can really upset our entire world, pollution and global warming. I want to point out especially that we in the U.S. are a problem. And you see on this graph how we compare, for example, in automobile mileage per gallon of gasoline. Look, we're a factor of 2 less than some of the better countries. Why is that? Well, think about it. Some of it is technology, but a lot of it is just attention. Our willingness to devote our attention and try to do better. So we've got a long way to go there in efficiency of our automobiles. And we've improved recently some, yes, but we've got a long way to go. The next transparency shows also how we do in pollution. This is a pollution amount of CO2 per person. And you see that we are enormously worse than most other countries. The United States is at the top. And we're several times bigger than the countries down below. Now, some countries like Switzerland uses a lot of water energy, which they have an advantage of. But there are a lot of other countries that we really ought to be competitive with, and we're polluting a lot. Some of this is because of our great wealth, that we just don't care, we use a lot of energy and so on. But much of it is because we don't pay enough attention, and we should. Now, in helping these things, science and technology are very important. Science and technology are very important in finding ways of saving energy, being more efficient, emitting less CO2, and so on. These are very important. And I'm delighted to say that I think UC Berkeley, particularly LBL, has been very helpful in this respect. 30 years ago, Art Rosenfeld, a professor of physics working at LBL, decided, it's time to really start working on energy. This was the time of the 1973 crisis. Time to start working on energy. So he began to devote himself to it, and he's had, I think, a very profound effect in California, at least. He's now on the commission, Energy Commission of the state. He's advised the governor for a long time, and I think it's made a very big difference. In addition, you've heard some of Steve Chu's discussion of what LBL is doing. And there's a guy, Levine, at LBL, who works hard on this, and he spends a third of his time in China. Why? Because China is growing rapidly, its use of energy is growing rapidly. They're emitting a lot of CO2 because of the way they do energy, and he's spending a third of his time helping the Chinese be more efficient, and I think, again, that's very important to all of us, and we have LBL to thank. And I think the rest of the campus are quite interested, and many people are working on it too, and it's important. Well, now, in California, particularly, we have made some progress. The next transparency will show how California compares with the rest of the United States. This is in the use of electricity, and you see that when the crisis came in '73, there was a sudden drop. There's the big oil embargo after '73. And then California flattened out. The rest of the U.S. stopped growing as fast, but nevertheless, the amount of electricity used per capita continued to grow. Most of the country, except in California, it grew very little. So we've done well in California. If the governor's paid some attention to it, I think Art Rosenfeld has had a very real effect. And this has been important. Now you see also it's a substantial amount of money, $400 per capita. $400 per capita, that's a substantial amount of money overall. Now, we're making other progress. The next transparency shows additional progress that we're making in the efficiency of various appliances. Refrigerators, for example. Now, you see these arrows. The white arrows indicate regulations put on by the state of California. The black arrows are regulations put on by the U.S. government. And those regulations have had some effect, and general emphasis have had some effect. And look at the efficiency of refrigerators. The index of amount of power they use has gone way, way down for refrigerators. The gas furnaces too, central air conditioning, all that has gone down. Now these are new devices. They haven't replaced all of the old devices yet, but the lifetime is the order of 20 years or so, and the refrigerators anyhow. And so in time, we will be replacing them, and we can do a lot. There are many other ways we can save energy. For example, in housing, the next transparency will show something about the effect of what kind of paint we use. That's the temperature of a roof, depending on what kind of paint you use. With black paint, the temperature in the sunshine raises about 40 degrees centigrade. That's much more in Fahrenheit. With white paint, only maybe 10 degrees or even less. With optically white paint, that's paint that's white in the ultraviolet too. So using a different kind of roof can make an enormous amount of difference. California has recently enacted a regulation about that. Now also the orientation of your house can make a difference in the amount of light you get, the amount of heat you get, and so on, and what happens. So thoughtfulness about design of buildings can do really an enormous amount. Housing uses about 35% of our total power. Housing does. Transportation uses a substantial amount, about 40%, and then there's manufacturing using about 20%, so on. Now, in addition, besides the fact we can save things, that saving is useful. In most of the things that I've indicated where there's been saving, where we've invested $1 of capital, we save about 30% per year. So you get a payoff in 4 or 5 years, complete payoff, and then from there on you're making a profit. So if we're willing to invest a little bit in the long range, we can do quite a lot, and it's very useful, not only in saving the climate, but also in saving money and maintaining our resources. Now our resources are finite, particularly carbon resources. They can last a long time, particularly if we use coal and so on. They can last a long time, but if we use at the present rate, we'll be using up the oil in the order of 100 years or so. All the oil, and the coal will last longer than that. But we've got to start paying some attention. What kinds of energy do we have? Well, we have nuclear energy, it's a possibility. There's solar energy. If we can find more efficient ways of converting light to electricity and batteries and so on. That needs some technology. There's wind energy, so all of these, nuclear energy has been mentioned, is certainly very big possibilities. So science and technology are very important aspects of understanding what can be done, but the intention of our society is a very important aspect. Intention of our society in being willing to make long-term investments and really doing some savings. California has done better than most of the rest of the country, but we can do still better. And we need to decrease rather than increasing. So those are our needs. The possibilities are enormous. It's a very important part of our total economy, very important to the future of humanity. Thank you very much.
As a representative of the dismal science of economics, I'll try to provide some perspective on the feasibility and cost of achieving self-sustainability in energy. The term dismal science itself comes from Thomas Malthus, who in 1798 expounded his law of the arithmetic growth of resources and the geometric growth of population. And what happened to the slide? Okay, here we are. He said the power of population is indefinitely greater than the power in the earth to produce substance for man, and the race of man cannot, by any effort of reason, escape from it. Pretty pessimistic. Malthus has been proven wrong to some degree so far. He did not anticipate that population and control and agricultural innovation would give us 2 centuries with some abeyance of his checks of crime, disease, war, and vice. However, the limits to fossil fuel revenues and global warming present a new Malthusian challenge. Man is probably incapable of attaining the self-sufficient status of species such as crocodiles and cockroaches, but with foresight and investment, we may be able to transit from unsustainable dependence on fossil fuels. In the past 50 years, the U.S. has not been self-sustaining in energy, and certainly not in clean energy, and imports of oil have certainly risen to about 30% of energy consumption. However, there is some better news. Energy use per dollar of GDP, the goods and services that we value, has been falling at more than 2% per year since 1973. Income today weighs less per dollar than it used to, and it uses less energy. Energy consumption per person has been relatively stable over the past 30 years. Gains in energy efficiency have roughly offset the effects of increasing income. Energy prices have tended upward over the past 3 decades, and these price increases seem to have moderated demand. Some of this is from direct demand response. More comes from the imposition of appliance building and vehicle efficiency standards. A threshold question for an economist is why energy markets don't satisfactorily control consumption and guide innovation in the same way that markets work elsewhere in our economy. Economic analysis of non-renewable resources shows that, at least with respect to the question of whether resources such as oil are getting used up too fast or distributed efficiently over time, if those are owned by a monopolist, then the monopolist should get it right. Our oil producers, such as OPEC, do have market power, but they do not seem to have the foresight of true monopolists. However, the primary reason that private energy markets are failing us is they do not take satisfactory account of the geopolitical and environmental risks that the U.S. faces. These risks will rise if we continue on our current energy trajectory. As world demand for energy rises, imports become more indispensable, and things heat up, literally. What are the prospects in the future for declines in energy consumption per unit of GDP or energy consumption per capita, declines that would bring us closer to self-sufficiency? First, increases in domestic fossil fuel production are unlikely for oil and gas. They are possible for coal, particularly if we can develop environmentally acceptable technologies for conversion to consumable energy. For example, it would be very neat if we could engineer an anaerobic bacterium that ate coal, sequestered carbon, and excreted hydrogen. Nuclear energy is environmentally clean as long as the reaction stays in its containment, but high costs of uranium mining and high capital, waste disposal, and shutdown costs continue to make it problematic. Biofuels have potentially a great future, but right now their energy balance is not that attractive. They're hard on the environment, and they take a lot of energy to produce. What about the so-called really green sources of energy, such as solar, wind, and hydro? Renewable sources today account for only 6% of energy consumption, and within this category, wood and hydro dominate, and those are not new technologies, and they don't have much potential for expansion. The new renewables, photovoltaics and wind, are tiny, and even if they grow rapidly, will have little impact on total energy supply before mid-century. Hydrogen and fuel cells are talked about as clean sources of consumable energy, but these are not primary energy sources. They have to themselves be produced. So where then can we look for self-sufficiency? The answer, I think, the best answer is to just say no to energy. This is the ultimate green renewable energy source. Each BTU freed up through reduction in consumption displaces a BTU of imported fossil fuel and also the capital cost of processing and transporting it. Conservation is not a will-o'-the-wisp, a good-sounding idea that's impossible to put into practice. Most of the stability in U.S. energy consumption per capita over the past 50 years is the result of conservation. And this is an environment where conservation has not been a particular priority, nor has it been particularly painful. California has led the way in improving the efficiency of energy consumption, and much of the innovation and impetus for this has come from UC Professor Art Rosenfeld and his team at LBL. More than any other person, Art Rosenfeld has showed how, as a practical matter, we could approach energy self-sufficiency in this century. These charts show that California is, of course, a large consumer of energy, commensurate with its size, but in terms of energy consumption per capita, one of the best states. One sees that in California, energy consumption per capita has barely moved this is Art Rosenfeld's slide, but it's too good not to show. Energy consumption in California has barely moved, saving each of us quite a bit of money in comparison with the rest of the U.S. What this slide does show is, I think, that will is an important factor here. Energy consumption is not immovable. If we have the will to do it, we can do a lot about it. So how was the energy proponents of California accomplished? Primarily through innovation in the energy efficiency of appliances and buildings and the imposition of efficiency standards in the California codes. Refrigerator efficiency was mentioned by Charlie Towns. It's improved 71% in the past 28 years, even though refrigerators have gotten larger. This did not require more expensive refrigerators. Their real cost has actually gone down by more than half since 1973. And I don't think it's not done yet. There's more opportunities here. One of the greatest opportunities is in automobile vehicle efficiency standards. These are set at a national level. They've crept up because of the importance of the sector. This has been very important for moderating energy demand. But the exemptions for trucks, which includes pickups and SUVs, is limited to overall vehicle efficiency gains. There are huge opportunities for improvement in vehicle efficiency, even with conventional vehicles, and even more if we look to new hybrid and other technologies. Now, there are a couple slides which, again, borrowed from Art Rosenfeld, which show, I think, very graphically how much conservation can contribute to the problem of self-sufficiency. Compare the energy you save from the refrigerator standards alone with what you get from various sources of energy. And what you find is that energy saved from more efficient refrigerators is enough to replace 20,000 5 kVA photovoltaic systems, all of the conventional hydro in the U.S., or all of the renewable energy supply from other sources twice over, or it would account for about 25 of the nuclear energy system in the U.S., about 25%. If you translate that into dollars, it's even more striking because with conservation, you don't have the capital costs of building a plant to provide it. So refrigerator standards alone beat photovoltaics, hydro, renewables, and about 2/3 of the nuclear power industry. There are immense opportunities, I think, still to bring our energy demands down to sustainable levels simply through good conservation. Adoption of currently feasible energy efficiency standards across the U.S. would go at least 2/3 of the way to energy independence. These would simply apply California appliance and building standards nationally and impose motor vehicle standards at the best practices now prevailing in other developed countries. And I think this is just the beginning. Even here in California, I think there are many obvious ways that we can further trim energy consumption. How do we get to energy self-sufficiency? This is really the economics of it. First of all, a substantial carbon tax would make fossil fuel prices to users reflect their true geopolitical and environmental cost, reduce demand, and voluntarily encourage voluntary conservation. Revenue from a carbon tax could finance investment in conservation and renewable energy technologies. Tradable CO2 emission licenses would promote best use of fossil fuels. These kinds of licenses have worked very effectively in reducing pollution for other things. Finally, you can use energy vouchers, tradable energy vouchers, to make energy tax policy income distribution neutral. In sum, it should be feasible for us to achieve energy self-sufficiency and substantial restrictions on CO2 emissions by 2050 using primarily existing proven technologies for energy conservation and tax and licensing policies that are effective in making consumers respond to the true cost of energy. And this would also support research into new energy technologies, which we will need perhaps in the last half of the century. If we do these things, we can make the U.S. a safer, cleaner place and the world a better place. Thank you.
Ladies and gentlemen, good afternoon. I don't have PowerPoint to show, so you can pay attention to me rather than the pictures. Well, during the long history of the development of mankind, the planet Earth used to be regarded as an infinitely large space where one could never reach its end. The Earth was so immense with a limited population that the impact of human activities to the biosphere and the ecosystem seemed quite negligible. But in the 20th century, things changed dramatically. World population increased from 1.5 billion to 6 billion. Human activity intensified, and with the advancement of communication and transportation, the Earth has shrunk in relative terms. And now it is possible to communicate with people almost anywhere. It takes only a day and a half for a commercial jet plane to fly around the world. Advances in technology have made it more possible for people to drive and fly than ever before. And this number grows in leaps and bounds daily. At the same time, the Earth's natural resources has been substantially depleted, and the ability of the Earth to digest waste production by human activities has also become limited. This sudden transition from the perception of unlimited Earth to limited Earth has extremely significant consequences, yet The development of human society moving along the track of the infinity for a long time has not seemed to be able to adapt to the new reality that the Earth is limited. On the limited Earth, with so many people pursuing unlimited material comforts, perhaps the most important challenges for scientists are problems related to the use of energy and impact on a living environment. As the world is becoming smaller and smaller, challenges for each country to combat against a deteriorating living environment has become global problems. It must be seen as challenges for all humankind as well. Ozone holes, the global warming trend, and the reduction of sunshine hours by 15% in Asia during the last several decades due to particulate matters produced by the combustion of low-grade fuels are such examples. If we examine the world in its entirety, we find that it is, in fact, in many ways overdeveloped, especially in terms of the excessive consumption of natural resources and the damage done to our living environment. From the point of view, the emission of carbon dioxide by human activities and the consequent worsening of the global warming trend, the common practice of categorizing countries as developed, developing, and underdeveloped has become increasingly unrealistic. And even the so-called developing countries are often not sustainable, and these should all be categorized as overdeveloped. Unfortunately, every developing country has been attempting to follow closely in the footsteps of the so-called developed countries, obsessed with improving their material comfort without paying enough attention to the environmental consequences. That's why what the U.S. is doing is of extreme importance. At the present time, there are 6 billion people on Earth producing 24 billion tons of carbon dioxide a year. On average, that's 4 tons per person per year. The so-called developed countries and newly industrialized countries in Asia are producing about 10 tons per person per year. The United States and Australia are the highest, and 20 tons and 19 tons respectively. If during the next 30 years, developing countries in Asia, Africa, and South America were to catch up with developed countries, and if we do not change our course of action, then even if population on Earth does not increase at all, the energy demand will likely to double or triple in the next 30 years, a demand that will be increasingly difficult to meet and could have potentially catastrophic environmental consequences. However, if the advances of science and technology will enable us to improve energy efficiency by a factor of 3 in the next 30 years, this is certainly possible, as you have heard from the previous speakers, we might be able to maintain the emission of carbon dioxide at the current level, but it is certainly still too high, and the development of human society is not going to be sustainable in the long term. That is the reason why it is extremely important for us to develop renewable and clean energy sources at the earliest possible time. If we consider the fact that the total energy consumption of human society on Earth is only about 1/10,000th of the amount of energy which the sun transmits to the surface of the Earth, maybe the time has come to give added degree of urgency to finding ways to replace the current usage of fossil fuel with solar energy. However, many of the problems that we face today are problems that cannot be solved with current scientific knowledge and technologies. They await the accumulation of new scientific knowledge and the development of new technologies. That is why it is so important to continue our effort for the advancement of science and technology and for the education of a new generation of creative scientists. That's what Cal has been doing. Certainly, we cannot go on as we have been. Things have to change, and we are the ones who must make it happen. Not we, as in the people who are up here speaking to you today, but we, as in everyone in this room, and everybody walking around outside, and everybody who thinks tomorrow should be a little bit better than today. We have to face the problems resulting from energy usage and its impact on our environment. We are to achieve sustainable development for the entire world. We must increase energy efficiency. This is really the first priority. Reduce dependence on fossil fuels, develop renewable energies, maintain biodiversity, make a more careful examination on population policies, and reduce the consequences of all human activities on our living environment and ecosystem. In a sense, what we need to reestablish is the harmonious relation between humanity and nature, a relationship that became disjoint after the onset of the Industrial Revolution and when human society became increasingly dependent to the point of addiction to the energy from fossil fuels. While the reserve of fossil fuels is limited, the power of the sun, on the other hand, is virtually unlimited, at least for next several billions of years. After 4.5 billion years, the diameter of the sun will expand to the diameter of the orbit of the Earth, and we might disappear altogether at that time. And it is time for us to find our way back to the power of the sun. The 21st century will be the critical turning point for mankind. I'm quite certain that the globalization of the world economy will ultimately reduce the risk of military confrontations being used to settle international disputes. If what replaces military confrontation, however, is simply high-tech-based economic competition, then the tensions between the advancement of science and the sharing of technology, between economic rationality and the political passion of nation-states will not be resolved, and the advancement of science and technology will continue to be used as the tool of domination by some, rather than liberation for all. If, however, we learn to solve problems together, learn to share knowledge, new technological options, and the limited resources available, learn to respect and understand different cultural heritages, then it will be possible to realize the establishment of a genuine global village that enables sustainable development for all. We cannot change the past, but we are the ones who write the history of mankind for the 21st century. This is the first time in human history that all human beings have been faced with learning to work together and live together as one family or one community on Earth. The time for realizing that the planet Earth on which we live is only finite in space, capacity, and natural resources. This is a necessary awakening. It is vital for the survival and sustainable development of mankind. I believe that if we make the correct choices at these crossroads, then the 21st century is likely to be marked as the great turning point or great transition, the beginning of a new era in the history of mankind. And I hope Cal will take the lead. And we have to go beyond the national boundaries and look at the global program altogether. Thank you very much.
I asked to speak last because I knew that my colleagues know more than I do about this and many other topics. And so I'm relieved of the responsibility for showing you quantitative graphs. Instead, we learned a lot of important things from them. For example, that the efficiency of refrigerators only went up when there were state and federal regulations on the efficiency. And once we get this gadget going, I'll give you some other examples. The general pitch that I will try to present to you is that the free market is a wonderful mechanism, but it often doesn't work. And the refrigerator example is a good one. Another example is that we don't have any really fuel-efficient automobiles. They're all really extremely guzzling devices, and people generally don't buy small ones, and so the automakers say, well, see, there isn't any market for that. Well, the automakers earlier said, yeah, we know how to put seatbelts in cars, but nobody will buy them. They're not willing to pay the extra cost. And so to get seatbelts, it required a government regulation requiring them, which saved, I don't know the numbers, but thousands and thousands of lives per year. So there are times, democracy, free enterprise though we have, governmental regulation is the only way to do some things which we jointly think are important. I don't know if we're ready for the first slide. I don't see it here. Well, anyway, the general idea, the first slide. Well, it doesn't do much good, but my whole talk is in this thing. So I will just have to wing it. Is help on the way? Yes. I think I have it with me. Anyway, I will give you some dramatic examples of the general principle that very often we have to get together as a democracy and give our governmental organizations authority to make rulings in the national interest which do not result from our free enterprise system. And one example is that year after year after year, Congress has refused to improve the mileage requirements for automobiles and trucks. There's been a move in Congress. There's been a bill every year for 3 or 4 years running. Always it fails. The same thing was true for subsidies on oil. And for the first time yesterday, the Democratic Congress reduced, they didn't eliminate, but they reduced the level of subsidies for oil, which will make oil more expensive and give competing energy sources a better chance at being successful in the market. So tampering with the market is okay, then you let it run free, is the general principle that I believe. Here we go. So my first slide if you'll excuse the expression, a motherhood statement, which is, I think, that the theme of this session is that we got to get independent from oil. Now, it's true that we import a fair amount of liquefied natural gas, and I don't know the numbers, but I don't think it's on the same order of magnitude as oil. Why do we want to be free of dependence on imported oil? for political reasons, we now have to be involved in a lot of unstable dictatorships in the Middle East because we depend on them for oil. We have economic reasons, which is to have some control over the main source of energy and economy, and national security reasons because countries over which we have no control can cut off the supply. Wasn't it in 1970-something that there was an oil embargo, and that could happen again? Does someone have control of this? Thank you. So I'm going to take the general point of view, very much buttressed by my colleagues, that science is not the problem. That is, the technologies have been described which are either presently available, nuclear power. We can certainly build more fuel-efficient cars and trucks. We can certainly provide coal-burning plants with smokestack filters. It's pretty close to the stage where we can convert coal into liquid fuel. Now, that doesn't save the carbon balance, but it certainly saves the pollution effect. And so these are present technologies. Now, how did you do that? Okay. Now, here are some feasible technologies which are near term. And I have enormous confidence in my colleagues in the scientific community and engineering community to do these things if they're either mandated or economically advantageous. I already mentioned coal to oil conversion. We heard earlier that there are little microbes in the guts of termites which help the termite to survive because the termite can chew wood but can't digest it. And so these little organisms have been pulled out of the guts of termites, and there's a lot of genetic biotechnology development so that enzymes which had that humble source can convert waste agricultural products, cheap wild grasses and so on, to either glucose or ethanol. And we've already heard that wind and solar don't play a big role. So here's some of the complaints that I've registered previously, that Congress has repeatedly refused to mandate fuel efficiency for cars and trucks. They've refused to raise gasoline taxes to raise the price to $4 a gallon, which would reduce enormously the consumption by the use of smaller cars and limited driving. And the next point I already mentioned is that subsidies to the oil industry have been reduced. And the next thing is to provide subsidies to encourage development of alternate technologies. Now that's a two-edged sword. On the one hand, government funding of research is an extremely important tool, as we've heard in great detail. But also, once the research is done, we need to be sure that the end product will survive in the market, so that subsidies, at least to get alternate technologies going, with the assurance to investors that it will be a standalone success. So my main point is that the technology is there, or near term, as my colleagues have described. The real problem is political, which is for Congress to agree to do what's necessary to provide incentives when things aren't happening by themselves. That's it. I have the cover. Thanks.
Well, predictably, our speakers gave us more fulsome stories and very exciting and stimulating than we had originally scheduled. I would encourage people who have questions to hand them to the people picking them up. But first, maybe it would be, I'd like to hear, since there were both agreements and disagreements, and maybe Steve, since you started us off, if you could just make a couple comments on what you heard from your fellow panelists.
Thank you. I think there's widespread agreement that conservation and energy efficiency is the #1 thing that we can do and we can do now. Universally, that remains the lowest hanging fruit. Then beyond that, I think there are technologies, and again, that aren't being used because of policies, and ultimately, you're going to have to not blame the policymakers, your political leaders, but you're going to have to blame yourselves. I really mean that, because many of you really don't want the price of gasoline to go from $3 a gallon to $6 or $7 a gallon, which would definitely change habits. And many of you would not like your price of electricity to go up by 20% so that we can start to think of capturing the carbon in coal-burning plants. And so one has to give political leaders support when they even begin to think of those things. Jimmy Carter lost the election immediately when he suggested a 50-cent gasoline tax. It was gone as soon as he even suggested that. So I think the American public and the public at large has to really do that. Now, having said all those things, there are some opportunities in science, new technology that can really change the landscape. If we can store electrical energy effectively and then generate electricity on demand, then all of a sudden photovoltaics and wind is here now commercially viable, except for the fact we can't store it. And also it would make nuclear power plants much more useful, because once you put all the money and invest in that, you want it to run 24/7. It's the capital investments that's really the cost of nuclear power. The fuel is almost nothing compared to the capital investment. And you want it to do 24/7, and so in light load times, you want to be able to store it chemically and turn it back into electricity. These are areas which really need research, and then renewables like solar, if it ever gets cheap, wind, which is getting cheap enough, then become much more valuable. So there's a wide area of things, and there's not one solution. It's not going to be an economic solution. It's not going to be a scientific solution. But in the end, the public has to buy into this fact that if we don't do this, we're going to be very toasty.
We all seem to agree that nuclear energy is a big part of our future, but nobody mentioned the real problem, which is storing the radioactive waste from reactors. It's a serious problem. I'm not an expert on it, but I've read some popular articles that you can put some of these long decay life wastes back into a particular kind of reactor and cook them, which means bombard them with neutrons to change those long-lived isotopes into shorter-lived ones from thousands of years to hundreds of years. I don't know the status of it, but there was much optimism in some technical articles that would be done soon. But until it's done, that's a real black shadow over the future of nuclear power.
Let me respond to that. Actually, it's the current lifetime of nuclear waste, if we don't reprocess the fuel, is a couple 100,000 years that we would have to store it. Couple 100,000 years. With these these fast neutron reactors, you can reduce the lifetime by a factor of 100 to 1,000, the lifetime storage, so it becomes tractable. It becomes a few hundred years, and you can reduce the amount of waste by a factor of 10 to 30. But it's not commercially viable yet, and we would like to do much more research to make this viable. But right now, we don't have in hand the technology to make it commercially viable, but there is great promise. And he's absolutely right. Don Glaser is absolutely right. If we continue as we are now, we will have filled up Yucca Mountain by 2012. We won't have opened Yucca Mountain by 2012.
But then that makes it a political problem, right? And one of my Canadian friends points out that in northern Saskatchewan, where the population is 1 person per square mile, you could locate basically mausolea, which would accommodate all of the nuclear waste that North America would generate readily for the next century or so. So I think that's, in fact, is a solvable problem. I believe it's 100% exactly what George Smoot said, public perception problem, but I'm happy to hear people disagree.
I liked very much George Smoot's suggestion that nuclear energy, nuclear production, if it's done, should be done by a few really responsible companies, perhaps not including Halliburton.
It's definitely a political crowd.
And I think it would go a long way to making that potentially acceptable. But actually, I wanted to ask a question of the other Nobel laureates. The dog that didn't bark in this discussion was nuclear fusion. Is that not a technology for this century?
I might come. I have a couple of comments. One is on gasoline. You know, if we improve our efficiency, a factor of 2, which other countries have done, they're a factor of 2 better than we are, and we can afford $5 a gallon. If we increase efficiency, then we put taxes on to encourage efficiency. Now, as for fusion power, yes, in principle, we can get a lot of fusion power, enormous amount of fusion power available. In principle, we don't know technically just how to do it appropriately, and it wouldn't necessarily produce a lot of radioactive problems either. There are, in fact, enormous amounts of energy available. One from the sun, fantastic amount of energy from the sun, and Steve Chu has spoken about that, and there's maybe some ways of converting solar energy to power and batteries and storing it, maybe some way of converting solar energy into power through plants, which then can be converted in a way we have to find out to appropriate fuel supplies. So enormous amount of energy from the sun, enormous amount of energy available from fusion, too, if we know how to do it. But those will require science and technology.
I think the advances of science and technology, we could expect 50 years from now, a requirement of energy could be all satisfied by photovoltaic cell and biofuel. It means if you live in the United States, you do know that per square kilometers, there are only 30 people live in 1 square kilometer. So everyone will have enough sunshine to generate electricity or go through biocell to produce alcohol. But at that time, the richest country probably will be the country which is most less densely populated area. For example, Canada, 1 square kilometer is only 3 people, so they have more sunshine than the United States will have, 10 times. On the other hand, Taiwan has 600 people living in 1 square kilometer, so we have to work 20 times harder to get the same amount of energy level. And that discrepancy will make a big difference about geopolitical powers and where the energy will be generated more inexpensively. And there will be the energy exporting countries.
Okay, maybe I'll switch to a few of the questions from the audience. First one, which is a
Bob,
very...
could I suggest that you actually have Art Rosenfeld stand up, since we
Art,
quoted him so
stand up.
often?
No, art.
Art.
Yes.
Indeed, we've heard so much about energy conservation as being a significant part of the answer. That means we need to learn how to clone Art Rosenfeld. Actually, the first question is a variant on the light bulb question, which is, how many Nobel Laureates does it take to solve the global climate change problem? Anybody want to answer that?
That's a different problem than the energy problem.
Still a few more.
Yes.
So I'll change the wording of this slightly, because I think YT, you raised this issue, which is about, of course, here we can, to first order, address the challenges in the United States. But as you said, there are also challenges for underdeveloped and for developing countries. And what do you think will be required? Let's suppose we make all of the advances that were speculated about here, whether it's in changes in behavior or in new energy sources. What do you think will be the process for bringing countries like China and India and, let's say, Africa along, the continent of Africa?
I think if we concede that most of the developed countries have been overdeveloped and find a new way, then we can persuade India and China not to follow the footsteps of the United States, and that's the most important thing. So achieving energy sufficiency in the United States certainly will be setting a very good example. On the other hand, I do believe that unless we learn to work as one community for the entire world, our chances are very little that we will be successful in the coming centuries. And how can we do it? I don't know. Like European Union, is that the way to do it? If Turkey were to join European Union, or many countries who speak Turkish-like language will all join in, and gradually there will be European Union and American Union and Asian Union, and then gradually become a United States of planet of Earth. And that might be the only solution.
That would solve a large number of other problems as well. This is probably for Dan, but anybody's welcome to take it. We've had a lot of discussion about legislating behavior that will drive conservation. This person asks, is there an example when the market has acted for the greater good when it requires inconvenience for people?
You'll have to give me some time to think of a case. People do respond to economic incentives, and they do less convenient things when it's costly to do otherwise. I think the power of economics is there, but there was a comment made, I think, by Don Glaser that oftentimes the market doesn't recognize the economic opportunities, or consumers are slow to respond. For example, one of the things about energy appliances efficiency is that consumers are very skeptical of offers which say, pay more for this appliance now, and you'll save a lot of money in the long run. They don't buy fluorescent light bulbs, although that's certainly a characteristic of those kinds of bulbs. It takes, it may take mandates, requirements for a while to get people to recognize the economic value of these choices.
This person asks, suppose we were to increase the cost of gasoline in the United States to $10 a gallon, and let's say simultaneously produce 100% subsidization of mass transit. As two examples. Do you think one could estimate quantitatively what the benefit of drastic changes like that would be? That's anybody.
Besides a recession?
Well, I think the answer is yes, you could.
But you can't do that in a democracy.
Right. In a democracy, you probably cannot do that. Here's a final question, a technical question, which from any of the U.S. scientists, which are based on what we know now, what are the prospects for significantly increased photovoltaic efficiencies in the near future?
What are the prospects for its efficiency and cost? I think if you get 20% efficiency and you get the cost down, you're really there. And so what are those prospects? If you stay with silicon, the cost can come down by perhaps a factor of 2, but I would be very surprised if it came down by the necessary factor of 10. The nanotechnologies, we just don't know whether they're going to work. There's a path forward, but at least the ingredients are there that you can get the cost down by, in principle, a factor of 10. But until you have it, you don't really know. But it's worth betting a sliver of tax dollars on it, though. And when it gets closer, in fact, there are some startup companies that are starting that, but I think you also need some government-sponsored research, a mixture of that and venture capital.
Just a factoid, in the last 18 months, the net profits of the top 5 oil companies has been $169 billion. So if you think about that, there are a lot of resources there that might be some of which, even 1% of which, might be put towards addressing these issues. Let me thank all the panelists. For those of you, the very large number who did not get their questions asked or answered, we'll vet all of the questions submitted and post as many answers as possible on the Discover Cal site at a future date. So you are going to have homework to do. Let me just comment for the Discover Cal that the next Discover Cal event in Northern California will take place on Wednesday, March 21st in Danville, and on Thursday, March 22nd in Mountain View. At that time, the topic will be globalization and the flow of knowledge. And our featured faculty speakers will be Dean Annalise Saxenian, who's Dean of the School of Information, and Professor Stephen Weber, who's the Director of the Institute of International Studies. And you can learn more about the program and register by logging on Discover Cal, just like that, discovercal.berkeley.edu. So again, let's come back and thank all of the panelists for that.
Fundraising event, but they're also webcasting it, and they're going to have it on their webpage. So
Thank all of you for coming. There will be a reception downstairs in the Heller Lounge. If you can believe it, we have to run off to a photo shoot with Vanity Fair.